Everybody, we are back, and now we're on Pset 4 solutions. So let's go ahead and read through this problem. So I've created a fusion couple with two mystery materials, X and Y, X on the left, Y on the right, approximately 5 millimeters for each material, so 5 millimeters. After placing this material in a furnace at high temperatures and long times, the diffusion couple interface moved towards the X side. So that's strange, if we didn't know about the Kirkendall effect. So now we are asked, and actually I'm going to change my Y to blue. So what we're asked to do now is, let's draw the concentration of X and Y as a function of distance for several instances in time. So in order to accomplish this, we have to first start to think about what's happening in this system, and then what are the relative diffusivities and thus fluxes. So let's go ahead and get started. So what I'm going to do is actually answer this question a little bit backwards, probably answering number 2 in the process, because I want to figure out, and actually I want to kind of solve it essentially a little bit from the fundamental point of view. So what do I mean by this? So the interface is moving over here. So if I think of my planes or my atoms, so I have atoms here, and the X atoms, I should have drawn those red. Actually, I'll draw them red right now. So I have atoms like this, all over here that are red. I have atoms that are blue. And for some reason, the interface, and I know that there's some vacancies as well, the interface is moving this way. Why is that? Well, that kind of seems to indicate to me that more of these red atoms, or basically the red atoms are moving this way. They're filling up these planes here, creating extra planes. There's vacancies left behind here, extra planes that are killing a lot of these red atoms that move. And so, again, we're going to get expansion over here, contraction over here. So basically, I could say that the diffusivity of X is greater than the diffusivity of my Y. So if I know that, I also know that, basically, if I look at here, I know the sum of the fluxes in the C frame. Let's zoom out a little bit. I know that basically this relationship, the flux of X plus the flux of Y plus flux of my vacancies must be equal to 0. I'm going to have a huge flux because I know that my flux is basically equal to minus d grad C. And if my diffusivity of X is greater than there, so that's my flux here. My flux in the Y direction will look like this. And then my flux, I'm just going to do green for my vacancies, will be like this. It's just true because vacancies are essentially moving over here to kill that extra half plane. So that's what we're looking like here. So if I look at over time, so initially, back to the original question, X will look like 100% X and then like this. But over time, they will start to kind of diffuse over like this and then like this. Now, for my Y, same thing, at time t equals 0, they're just flat. But it's going to take a little bit longer to kind of diffuse in. So it's going to take a little bit. It's not going to diffuse through as rapidly. So that's effectively what that X and Y profile is going to look at. So number 2, fluxes, magnitude, we already talked about that. Planes are being, again, created over here, destroyed over here. Describe that atomistically. Where will Kirkendall pores form? They should form on the X side, as long as we have, again, high enough temperatures and long enough time, little t. Excellent. So let's keep moving on. X appears to be a very promising material, but can become extremely brittle when C diffuses into the surface. The material X is most commonly utilized, has a thickness of approximately 0.3 inches thick. So I want to, very interesting, I need to kind of control when C diffuses in. Material X is most commonly utilized, has thickness of approximately 0.3 micrometers thick. So even at 0.3 micrometers, we can make our, basically, diffusion of materials in here, semi-infinite assumption. So I'm just going to kind of look at it like this. So this is my X material. I've got C basically floating into here. I'm going to make my semi-infinite assumption. So infinite here, X equals 0. If I'm just putting in my boundary conditions, so what's my ODE? dc dt equals d dc squared dx squared, or more generally dc dt. This is fixed second law, d grad squared c. So that's my ODE. My PDE is the one that we've worked with previously, remember? So remember, this, we don't want to solve PDEs in this class if we don't have to, because, well, it's going to take a lot of work and we don't want to solve that. But remember, we introduced the term eta. Eta is equal to x over square root of 4 dt. That was our substitution that we plugged into our PDE. Why is it a PDE? Because, well, I've got a function that is with respect to one variable, concentration with respect to x and t. So I've got two variables that we're working in here. If it's an ODE, there's only essentially one variable here. So this is a PDE that's second order in x, first order in t. So we did in class, if you remember, we substituted in, we created that dimensionless variable eta, and then we were able to convert to a much, much nicer, or at least a more manageable expression effectively. So remember that we saw that d squared c d eta squared plus 2 eta dc d eta equals 0. That was our basically ODE that we're going to solve. What are my boundary conditions? Well, I know that my concentration at an eta equal to 0 or an x equal to 0 is going to be equal to, my concentration of carbon is going to be equal to 1. My concentration at an eta equals infinity, because it'll never reach there, will be 0. So again, this is a second order ODE, so I need two boundary conditions to solve this. What solutions is this, or what times is this solution valid? So remember, when I make this semi-infinite assumption, I am basically saying that the length has to be greater than 10 square root dt. So length is going to be 0.3 micrometers. So whenever, again, we need to know the diffusivity of carbon, and then we can solve or actually basically make that true. We want to make sure that the material X does not become brittle. If we are operating, and actually it seems like you could assume here, although it's not very clear in the problem set, but we can assume basically when carbon becomes that, basically 0.3 micrometers thick, then all right, we're in big trouble. So if we're operating at a temperature, so my temperature equals 800 K, and let's see, where's my carbon? And the activation energy for carbon is 10 times less than that for iron. This is a good problem, if I don't say so myself. So this is my operating temperature. I need to make sure, and I'm going to use my engineering approximation. So if you remember, if we're just kind of making sure that the penetration depth doesn't basically, go beyond a certain depth, we said that x equals 2 square root of dt. So I know my x, that has to be 0.3 micrometers. Where are we at? 0.3 micrometers. I need to figure out the time, and I need to figure out d, the diffusivity. But d is equal to d naught exponential minus qa over kt. K is going to be, again, our constant. And now we can start to, and we're told that the activation energy of C is 10 times less than that for iron. So let's figure out what's the activation energy for iron, and then we can make some assumptions. So let's go ahead. I'm going to say iron, let's say at 900, I'm 10 to the minus 13 meters squared per second. And let's say at 800, not 800 quite, let's go to 700. Let's say at 700, I am 10 to the 16. So I've got two diffusivities. So let's say diff equals d naught times exponential minus qa divided by k times t. We know that k is equal to 1.38 times 10 to the minus 23, and we're going to kind of substitute in for this expression. So I'm going to solve, because I have two unknowns. I know temperature, I know the diffusivity, but I don't know the qa, I don't know the d naught. So I'm going to solve that. Basically, I'm going to take, so I'm going to say diff1, or actually let's say diff 900 equals diff slash dot, and I'm going to say that diff, actually, I'm just thinking of a way to elegantly put this, but that may not be the best way to go about this. So I'm going to just do that. I'm going to say that diff, so 10 to the minus 13, I'm going to set that equal to diff slash dot t goes to 900, and then because I'm going to basically say, I don't need that, I just do this, this because this, and then I could also say that 10 to the minus 16 set equal to diff slash dot t goes to 700. What does this look like? So let's just pull this out. I'm basically setting this equation up like this, like so. So, and then I'm going to solve for my two unknowns, basically d naught, and I'm going to solve for qa, and I want the real solution. Actually, real. Let's see if it solves. Numerically solve for Q and the real solution. So occasionally Mathematica will kind of freak out here. And whenever you're doing these exponential functions, it really is not liking it. But I think that I have a syntax error for some reason. I think the problem is in this solve function. We may be able to do, I think we can do this. Could do an and. We can actually 3 times 10 minus 23. What may be asking. It may want me to pull out the function, but or I could have a little error here. But I see the error right here. So you got to be careful of your syntax equations. And now we got it. So this is my D naught, this is my QA. The problem says the activation energy is 10 times less. So I can just say that here my QA is equal to this, basically here. And then we'll do the full thing divided by 10. And I'll assume that my D naught is exactly the same. Is that a good assumption? Who knows? But I'm going to, the problem doesn't really prevent me from doing that. So diff, and I'm just going to do slash dot, t goes to 800. So this is my diffusivity. Diff of c is this. My x was equal to 0.3 times 10 to the minus 6. We got that there, and now I could solve that x set equal to 2 square root of d, or diff c times t, and then solve for t. So not very long. So the time will be very, very short for that. So we've got our solution, basically. All right. So now we're on to number 5. So we'll see if that assumption was really valid or not. But we solved our problem. It was a nice one. All right. Now let's go to our favorite types of problems, the problems that will show up on our exam, our Kroger-Vink notation type problems. So let's go ahead and get started. All right, so let's go ahead and get started on number 5. So it is saying that I'm working with Al2O3. I want to dope this material with CaO. So basically I know that this is my host. This is my impurity. Al2O3 can form anion, cation, and cation Frankel defects as well as Schottky defects. Activation energy for anion is 3, Frankel 4, Schottky 0.8. Draw and label how the natural logarithm of the concentration of oxygen vacancies and the diffusivity of oxygen varies as a function of temperature. Actually, a function of temperature, inverse temperature. Label axis regime. So we want to eventually, I'm going to scoot out just a little bit more. I think that's my limit. We want a plot of how does the natural log of the concentration vacancies of oxygen, so we know that's 1, 2. How does that vary versus 1 over T? We're going to have our intrinsic at high temperatures, our extrinsic low temperatures, and then natural log of the diffusivity, of oxygen, 1 over T. And we're looking for those slopes as we usually do, intrinsic, extrinsic. So let's go ahead and let's start up here. So I know that my dominant defect is Schottky for Al2O3. So I need to do my first step. Null goes to vacancy of oxygen, 1, 2, plus vacancy of Al, which is going to be 1, 2, 3. There's going to be 3 here. There's going to be 2 here. Good. Second step. What do? I need to write my equilibrium expressions. Okay, Schottky is equal to, remember I bring out basically concentration of my products cubed times concentration of Al squared equals exponential minus G formation of Schottky over KT. That's it. 3, what is my, I need to write out my electroneutrality statement. And what was the trick I showed you? What do? You bring out the charge in front. So 2, 3. Let's do, again, we're going to only do this once. We've already had to suggest to ourselves do this in class, but let's go ahead and say, like, do a thought experiment. So let's say I have, for example, let's say my concentrations of vacancies of oxygen is 3. So 3. So my total charge is going to be plus 6. So I've got 3 here. So if I've got 3 here times 6, right? Then I divide it by 2. So what's my, basically I'd find that my concentration of Al, 1, 2, 3, is equal to 2 minus 6. Therefore, I'm good to go. So remember, don't bring out the charge right in front of the element. So that's my electroneutrality statement here. So now I need to rewrite my expression because, again, what am I interested in? Vacancies of oxygen. So I need to substitute and get rid of this Al here. So I'm going to end up with an expression that is V naught cubed, and then it's going to be basically, so for example, I'm going to substitute in 2 over 3 V naught squared, and that's going to be proportional to exponential minus G formation of Schottky over KT. Remember, because eventually I'm going to be pulling this out anyways, I'm just looking for the slope. I'm just looking at the proportional relationship. So I'm going to end up with something that looks like V naught, V naught 1, 2 to the 5th power is proportional to exponential, I don't care about the prefactor stuff, over KT. So I'm plotting 1 over T, right? I'm going to put in the natural log here. So natural log, this guy, I'm going to already get rid of that before I even do the natural log is here. Once I do the natural log, I get rid of this here. So I'm left with an expression where I have my, basically, y, which is this, my 1 over t, which is x, and then the slope is this minus gf f of s over 5k. So I'm going to do this. So this is going to be, my slope here is going to be minus g formation of Schottky over 5k. Actually, I'm going to do it on the other side. So remember, I just take out that 5. This is just math at this point. So minus g formation of Schottky over 5k. So that is approximately, or actually will be the value of that slope. Excellent. So that's just the intrinsic side. What about the the extrinsic side? Well, I am doping it with CaO, so that goes into Al2O3. I need to have, as one of my, because again, I'm looking at the concentration of vacancies of oxygens, I need to have vacancy of oxygen, 1, 2, and then I'm going to put in my substitutional cation. So Ca replaces Al. Al is 3 plus this here, so that's this. So I need to have, let's see, I need to have 2 of these. So now that I have 2, 2, and then I need to have plus 2 oxygen, oxygen X. That is my reaction. I don't need, because I'm putting in the energy, there isn't basically a formation energy associated with this, or a negligible one. So I just need to do my charge balance. 2 is equal to CaAl minus 1. And then there is no relationship with temperature, so this is going to be flat. Great. Now, my diffusivity equation. Diffusivity, we've learned, we can write that expression as basically this kind of gamma prime times my r squared times basically this F factor, this is kind of your jumping rate, times my number of sites over 2D. So remember, correlation factor, this is distance, this is dimensionality. My hopping rate, that is proportional to exponential minus g migration over kt, so that will be important, and the number of sites is important. So again, I'm looking how the diffusivity scales with temperature. So number of sites, what's my number of sites? Well, if I'm looking at the diffusivity of oxygen, that's going to be proportional, or actually basically my number of sites is going to be the concentration of V naught right here. So if I'm looking at the intrinsic regime, I do have already a relationship that scales with temperature here, and I'm multiplying by this, so my slope here will be this minus g formation of Shockey over 5k minus g migration over k. And in the extrinsic regime, well, this obviously isn't dependent on temperature, but we will have some slope because that is going to be minus gm over k. So there we go. Now I'm going to do my new, it's taken me how many years? And now I realize I can just do this and delete it. Oops. Except now I did that. So actually, here, let's just do this. I'm going to grab here. Let's just delete everything here. Hope you enjoyed it. All right. Let's zoom into our next problem. But it's going to be very similar procedures here. So I'm going to try to do over here. Working with TO2, that's my host, doping it with that. Forget the AL here. TO205 can form anion, cation, blah, 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 blah. We see that Shockey defects are my dominant reaction. Draw and label how that, again, I'm looking at oxygen vacancies. So let's go ahead and get to it. So natural log, vacancies, oxygen, here, 1 over T, again, intrinsic, extrinsic, diffusivity of oxygen, natural log. Again, natural log comes out because it's just math and plotting. Intrinsic, extrinsic. All right. So, Shockey is my step. So again, same thing. So my intrinsic reaction is going to be null, goes to vacancy of oxygen, 1, 2. Let's cap that. Actually, let's not cap that. What am I doing? Vacancy is oxygen, 1, 2, plus vacancy tantalum, 1, 2, 3, 4, 5. There's 2 of these, 5 of these. Good. I'm going to write my K Shockey, which is going to be V naught, 1, 2, to the 5th power, times vacancy tantalum, 1, 2, 3, 4, 5. Second equals exponential minus g formation Shockey over kt. I need my electron neutrality statement, which is just going to be 2 V naught equals 5 VTA for what am I going to do here? Well, I am going to now basically get into it. So I'm going to rewrite that expression again. Again, we've kind of done this before. I'm going to plug this in, but I could kind of already see that V naught to the 7th is going to be proportional to exponential minus G formation of Schottky over KT. So I'm going to redo that math, put the 7 down here. I'm going to do my natural log here. I'm going to get rid of this. This is my y. This is my x. So in the intrinsic, my slope was just going to be minus G formation of Schottky over 7K. Excellent. Extrinsic reaction. I'm doping it with V2. What is it? V2O3? Yep, V2O3. V2O3 goes into TA2O5. So I'm going to do, I need vacancy of oxygen, 1, 2, plus vanadium onto tantalum. 5 plus 3 plus is minus 2. And I think I'm going to need, those are confusing notations, but so let's just do 2 of these, 2 of these. So we're charge balanced. We're okay here. Plus 5 to plus 3, or minus 2. Good. We need plus 3 oxygen, oxygen X. Good. Good. We're all good to go. What's our electron neutrality statement? Concentration vacancies of oxygen 2 equals 2 vacancies. Not vacancies, but vanadium on tantalum. There we go. We see that there is no relationship here. When we have diffusivity, remember, we have to tack on this minus G migration over K because of that relationship we wrote previously over here. And then extrinsic, there's still no relationship with temperature here, but once you have diffusivity, you add that migration term, and that's all she wrote. So that is problem set 4. So study hard from problem set 5, get ready for exam 1, and let's get ready to go. All right, if you have any questions, please let me know. Thanks. See you next time. Bye.